Hello everyone, welcome to Learning Express YouTube channel. Friends, today we will continue CTQ10. The part 1 was completed previously where we have discussed or we compared these two circuits depending on the gain calculation. Okay, so in this particular video, I'll discuss these two circuits gain calculation and swing possibility uh, depending on this current sources as a practical element. Presently, in the previous discussion, we have taken the current sources as ideal, but here I will take the current source as a practical current sources. Okay, so we'll consider practical current sources. So, depending on this, we will analyze the individual circuit gain. Then we will see what exactly the output swing is. Okay, so let me draw the circuit first. Then we will see the gain calculation. Okay, so what the circuit one? Actually, we have two current sources. So this is the complete differential structure. Okay, yeah. Okay, so this is 2 I naught, I naught, I naught. This is our V in 1, V in 2, and we are taking output here. V out 1, V out 2. Okay, so now the current sources are practical, or I'll say it is implemented by PMOS. Here we are using some P bias. I'm not telling here how to generate this P bias, but we are using this P bias as a biasing voltage. So this is external biasing, external biasing. This biasing technique I'm not discussing here. Okay, yeah. And this current source, the tail current source, is implemented by NMOS, so which I call N bias. Again, I'll say I am not discussing this biasing scheme. Okay, so this is also external bias, external biasing. So now point is that first of all I will tell you a little bit about the sizing so that further I will calculate the gain and other parameters. We will see what is the importance of that. Okay, so if I am sizing this transistor or current source by keeping I naught across it, and I am sizing this transistor by keeping 2 I naught across this, and what I can do, actually I want this transistor to allow I want to allow this transistor to flow 2 I naught across it. Okay, so what I will do, okay, so for the transistor who is allowing I naught current across it, if I'm using a size of WIL, then for a particular overdrive voltage, what I can say, I have I naught as a current and WIL as a size. Okay. Now, if I want the same overdrive for this transistor, and I have 2 times current, then what I will do, I will simply make 2 times W by L and I naught as a 2 I naught, so that again the overdrive is same, which same as previous one where we are allowing I naught. So for that we can see the relation. The simple relation in the saturation is ID, that is Kn dash by 2 WIL. VGS minus VTH is nothing but V overdrive square. Okay, so just to keep the overdrive voltage same for your tail current and the current source as a load, so I want to keep same overdrive. Let's say, for example, if I want to keep the overdrive of 200 millivolt, then for this particular value I have some ID which is nothing but I naught. I have some W which is nothing but or I can say I have some WIL of this, suppose n transistor is WIL. Okay, L is L minimum. Now, for the transistor across which the current is 2 I naught, so if I want to keep the same overdrive of 200 millivolt, then what I will do simply ID as 2 I naught, and to keep this thing intact, what I will do, I'll change this IN2 2 times W by L. So from this relation, we can easily understand this thing. If I want to increase the current at the same time, if I'm increasing my W with the same factor, then need not to change the overdrive. The overdrive is fixed. So the point to make this is that now we want to see the practical values of means each node voltage, so that I will consider the overdrive here. Then we exactly can see how much your output can go maximum and how much your output can go the minimum. Okay. So okay, later, once this discussion is over, I will come to this gain calculation. Okay. So before that, we will clear this concept that how these resistors are influencing your swing. Okay. So now let. So now I'll use these practical circuits here or practical current sources. So this is some bias voltage which I call let's say point A, and this is my input pair. Okay. Here we have degeneration with the R, and here I have some NMOS current source which has some bias voltage, let I call N bias, and here I want to 2I0 to flow, so that what I will do, I'll make it as a 2W. Let L is same for all, so it is 2W, then they are W, and they both are W, and this A is nothing but what is this A? This A is nothing but P bias. Okay. Again, I am saying I am not telling about how to bias. This is the external concept. Externally, I am biasing it somehow, and this thing I will cover in some other video how I am biasing it. Okay. So as of now, just we want to calculate this swing in the presence of these resistors. Okay. So what you can see, if there is a common mode of, sorry, not a common mode, sorry to say, but yeah, if I want to 200 millivolt as a common mode, sorry again, not a common mode, it is the overdrive voltage, and here also I want 200 millivolt as a overdrive voltage, and what I can see, let VDD is my 1.8 volt, and what you can see from the half circuit also, no need to see as a half circuit, but yes, the maximum that your output can go, let if I talk about the only output one, maximum it can go is your VDD minus overdrive voltage of our device, which I call the P. So it is also 200, so 1.8 volt minus zero point 0.2 volt, which is 200 millivolt, so it is your 1.6 volts. So in the presence of in the presence of practical current source, that is means some PMOS current source, our output is not allowed to go above 1.6 volt. If our output is going above 1.6, it means we are crunching the above devices. Okay. If output goes, if output, let's say single sided output, which is V out 1, if I am taking this circuit as a symmetric circuit or half circuit analysis, then if V out 1 goes above 1.6 volt, it means the PMOS device, PMOS current source device is crunched, or crunched means to say it will be forced to enter into the triode region. Okay. So this is the point that I want to make here. So this thing we will see when we are looking for the lower side also, that what we are seeing, that the minimum value of, let's say, x node. So what is the minimum value of x node? This is again nothing but Vx. If I call it minimum value, is nothing but overdrive of your lower transistor, which I call the M naught transistor. Let's say this is the M naught transistor. Okay. Yeah, which is nothing but 200 millivolt. So one thing is clear, that I am not allowed to go beyond this value at the point X. Okay. Now what about this value? This is nothing but I naught R. Okay. Yeah. And what about this value? This value is nothing but VGS of 1. Let it call M1. M1 is called M2. Okay. So what I can say, we input 1 minimum value. This time telling, this is nothing but a talk about common mode analysis. or I am talking about some DC voltage value. Common mode value. Common mode value is nothing but biasing voltage at this node, because we need biasing before applying any signal now. So this V1 is it is looking like it is some say AC signal, but as of now I'm talking about some DC signal, which is a common mode signal. Okay, I'm talking about the biasing voltage. Yeah. So what is the minimum value? It is nothing but the VGS of transistor 1 plus this I naught R plus this overdrive voltage of transistor M naught. Okay, so it nearly comes at, if I write it, the V overdrive of 1 plus VTH of 1 plus V overdrive of 0 plus this I naught R. So in DC we can see that this is an extra factor which is coming for this particular structure because of R, because of this resistor R. Because in DC analysis, this resistor is playing its role here and it taking the drop of I naught R, so that I can say the common mode is limited. Okay, so the lower range of common mode is limited, and when this create problem, when some other circuit is driving this circuit, that particular circuit will see a lower common mode swing, mean the output of that particular circuit which is previously used to it. Let me clear this concept. Okay, so suppose this OTA is used here and it has two inputs, okay, which is a V in 1, V in 2. Okay, so one thing, if it's a lower value that I call the minimum value of common mode is higher, suppose. Okay, so this is the common mode. Now, if some other block is driving this particular block, then what it will see some higher common mode. Means if the output of this particular circuit, which is called the dashed circuit, if the output of this circuit is swinging beyond the common mode limit of this, let's say this is our block, this is our OTA structure, or not OTA, this is our present structure, our present structure. Okay, so if I want to drive my present structure with some particular circuit whose output swing is good, then by seeing it, we can say the common mode swing for our circuit is less. It means it can take only the signal up to the certain level or above that. So it means when we drive our circuit with a particular any different circuit, then we will have some limitation of output means swing. So when we drive, I can write this thing like, when this circuit, which is present circuit, when this circuit is driven by some other circuit, some other circuit, there will be the limitation of, there will be the limitation on input that our present circuit can take, that our present circuit can take. Okay, so you do some homework on this thing and you will understand what these registers are doing. These registers are nothing but creating some common mode limitation here. So VCM min is higher due to this register. Okay, because here already we have minimum value of overdrive which of 0, and here we have this drop of I naught R in DC condition. So this voltage minimum value is little more with the factor of I naught R. On the other hand, if the same thing is seen for the circuit, let me draw here only. Okay, so here I have N bias where I am allowing only I naught. So the sizing is as a W only. Okay, this thing I am talking about the second circuit. So as I want to keep my overdrive same, so if this is I naught, I'll reduce the size to W only. Okay. As the current is I naught, so the size is W, and the current is I naught, the size is W. Okay. So this point has the overdrive what it was previously. So let's say this is minimum of this node that I call X, we call Y. As we can see, the circuit is symmetric, so Vx equal to Vy, and the minimum of these is equal to the overdrive voltage of the transistor M naught. Okay, so which is nothing but 200 millivolt. Okay, so what we can see from here, that common mode minimum value is what? Minimum of the common mode from this circuit. If I, yeah, extend this thing here, so for this circuit, what is the minimum common mode value? It is nothing but VGS of 1 plus directly overdrive of 0. Again, I will write it as V overdrive of 1 plus VTH of 1 plus V overdrive of 0. So this is this much voltage only. So we can see in the previous, the extra factor was coming here. What it was? The extra factor was coming like VCM. Minimum was V overdrive 1 plus VTH1 plus V overdrive 0 plus some extra factor I naught R. Okay. So this was the minimum value our circuit can take at its input in the previous circuit. So what we can see in DC, this register is not playing any role. This resistor 2 are not playing any role. Okay. AC wise, we will see while we calculating the gain, we will see. But as of now, we should understand the common mode perspective of both the circuits. Okay. So what you can see, what is the problem? Okay. With the first circuit is the common mode analysis that I told you here. But if you want, I can take it again one with the two circuits. Let's say this is my actual circuit, and this is my circuit one. This is my circuit one, and this is my circuit 2. Okay, so what it can take, let I only talk about one input, not I'm talking about two inputs. So let's say this can has the minimum of DC of this. Okay, let's say it can take the minimum of 1 volt, and it can take the minimum of, let, zero point 0.8 volt. So what we can see, when we will drive our circuits with some different circuits on backside, that what we can see, it can the circuit who is driving it can take the value 1 volt down. Let's say the common mode of that output is suppose 1.6 volt. So what will take 1 point till the 1 till 1 volt, and how it can go, let's say with that symmetric swing, it can go above 2.2 volt. But rather for the same circuit whose common mode is 1.6 volt, it can have these access to zero point 0.8, then above also it can go zero point 0.8, let's say symmetric swing, so it can go above like 2.4 volt. So what I can see, at the input there is a possibility of larger swing, or we can drive our and the, or we can say we would have the flexibility when we drive these circuits with the common mode point of view. Okay, yes. One more thing, now we'll see, is there any effect in this higher value of outputs? So from both the circuits that we can see, we are using here PMOS current bias, so this is P bias, and the same common mode is used for this. So what is the higher value that you will see? One is this circuit and bias. Okay, now, so I should see this VCM max value. Okay, so what can be the VCM max? This is your V out 1, this is your V out 2, VCM max. So need not to analyze from both the sides, either side is good. Okay, so what we can see, for this device, the minimum value that this output node, the maximum value that output node can go is what? The maximum value the output node can go is your VDD. So what this maximum, the common mode wise I am talking about, this maximum is always talking about the DC things. Okay. So what is the maximum value of output is nothing but VDD minus the overdrive of PMOS, which is nothing but again 200 millivolt, which I am writing as overdrive as of now. Okay. So now one thing that comes, if I am going higher than this, and what we can see, if this is NMOS and this node is defined some V naught 1 max, which is again DC, then this node, which is the gate node, can go at max 1 BT higher than this. Okay, so it can go 1 VTH higher than this drain node. Let's say whatever the source connection, I'm not worried about it. So this is the basic thing that we have analyzed. The maximum okay gate voltage V gate max can go V drain max, let's say plus 1 VTH up. So this is the maximum condition for saturation condition. This is I told, I think this thing I told in some other video, saturation condition. So if my gate voltage goes beyond this value, VD max plus VTH, then I can say our transistor will enter into triode region. So what we can see from here, now you see the swing, not swing. As of now, only I am talking about the maximum common mode, which is nothing but V over V1 max plus VTH of 1 in the input device. What is this? This is nothing but VDD minus V overdrive of P plus VTH 1. Okay. So this is the maximum value or input common mode can take. So in the maximum case, both the circuits are behaving similarly. Means both circuits are same. Okay, so this is the viewpoint for the circuit when we are analyzing it on the basis of like practical current sources, and we want to analyze on the basis of common mode voltage. Okay, so as the common mode voltage is decided, so what you can see, if I want to see the output minimum value, okay, we have seen the output maximum that can go 1 VT down. What is the output minimum value? Okay, so that we have to see. So any particular value of the common mode which we have selected, if I want to talk like what will be the minimum value of output, let's say output common mode minimum value. So whatever the common mode we have at present, VCM here. So this voltage minus 1 VTH of this transistor 1 is nothing but a minimum value of your output. So if I have biased my these input transistors with some value which is greater than with some common mode value which is greater than this minimum common mode value, then I can say that minimum common mode value minus VTH1 is the minimum output common mode value. Okay. So let's say I am biasing my input transistor just at the edge of the minimum common mode, which is nothing but zero point 0.8 in this case and 1 volt in this case, which is simply nothing but this overdrive plus this IR plus this VGS times, which is the minimum value. And if I am biasing my input pairs at that minimum value, then what can be the output minimum value? It can be nothing but the 1 VT down. Okay. Or the other way that you can see, the minimum value of output is what? Yes, that's great. Okay, so any common mode value minus 1 VT. So this is the perspective when we talk about this large signal behavior, not exactly large signal behavior, the common mode analysis and the swing perspective when we are considering the practical current sources. Okay, so I think in this particular part I should cover this thing. And next we will continue and you'll see in what which circuit is better in terms of gain. We already have seen with the ideal sources, so nothing is going to change when you consider the practical current sources. So from the gain point of view, it is going to be same. Let me tell you about the gain perspective. So it is not a point to say next class. Let see it. Okay, just I'm giving the point. Okay, how we will calculate the gain. So it is just like a practical circuit, or it is like an ideal circuit where we have considered the ideal current source. Now I want to consider practical current sources. Okay, so these are some P bias. Let I call PV, PB. This I call N bias, so I call NB. This is my V in one. This is my V in two. Okay, so if I want to calculate the differential gain, which is nothing but the differential gain is what? Let you call it differential gain. What is differential gain? Differential gain is V out 1 minus V out 2 divided by V in 1 minus V in 2. Okay. Yeah. So yeah, before exactly going to that, I should split this circuit as a half circuit because the circuit is symmetric, so I can split it to the half and let I directly do the AC analysis. This is which I call let V in. This is R, and this point I should consider the virtual short. Okay, so everyone knows this thing. I need not to calculate again and again. So this is my V out 1. Okay, so for this circuit, what you can see, if I want to see the R down, okay. So one thing that I want to tell you here, first for calculating this gain, V out 1 by V in 1, let's say V in 1, okay, where V in 1 is nothing but plus V divided 2 that I call differential voltage, okay, from the small signal point of view, okay. So what is this? Every circuit has we know as GM R out. GM is a short circuit transconductance, and GM for this circuit is nothing but GM of your input pair, okay, or input transistor. And what is the R out? Your R out is this RDS, this is R up, this let call R down, okay. So your R out is nothing but R up parallel R down, and for this structure we know the R down. R down is nothing but GM1 RDS1 times R. Let's say this is a approximated resistor, okay. And what is R up? R up is approximated or nearly equal to RDS of, let this device call 3, this call 4, okay. So RDS of 3 R up. So more like R out, we can say nearly is equal to RDS 3 because parallel of RDS 3 and this big quantity is nearly RDS 3. Okay. So what I can see, this GM is GM1. So what we can see, V out 1 by V in 1 is equal to minus, this is called minus GM1 minus GM1 by, sorry, GM1 RDS 3. Same thing for this particular circuit can particular half circuit can be done. This is nothing but minus GM2 RDS 4. Okay, and from symmetric viewpoint we know GM1 equal to GM2, and one thing that we should consider for the practical symmetric circuit, GM1 equal to GDS2, GM3 equal to GM4, GDS 3 equal to GDS 4, and GDS 1 equal to GDS 2. These are some approximation that should be considered, and GDS is nothing but what? GDS is your 1 upon RDS. Okay, okay. So this way we can see what is V out 1. V out 1 is nothing but minus GM. Let I call GM1 equal to GM2 equal to GM. So minus GM RDS3 I should call RDS, minus GM RDS is called V divide 2. And what is your V second? Nagmat minus GM RDS minus V divide 2. So from here we can find V out 1 minus V out 2 equal to minus GM RDS VD. Okay, so this is nothing but actually I want this as a, this quantity is VD. So what we can see, V out 1 minus V out 2 divided by VD is equal to minus GM/RDS. Okay, where GM is nothing but GM of transistor 1 comma 2 input pair, and RDS is nothing but RDS of transistor 3 and 4. Okay, so where what is the VD? VD is nothing but V in 1 minus V in. So this is the way of calculating the differential gain on any gain for any block. It is a GM R out. The GM short circuit transconductance, and R out is the net impedance looking at the output. Okay, so this is the DC gain calculation for any particular circuit. And for the second circuit, there is no difference because what is the circuit? I'm just drawing the the part DC wise. Sorry, AC wise. I'm drawing the part. So this is R. The two R I have split it like this, and from the symmetry viewpoint, I can take the virtual shot, and this is the way. So what is above that, what is lower than that, you can see. I can calculate V out 1 here, I can calculate V out 2. So from AC viewpoint our circuits are same. Okay, so here some resistance, here some resistance due to the current sources. Okay, so AC wise both the circuits are same. Gain of both circuits, gain of both circuits is same. Swing bias, swing bias, circuit 1 is uh, poor, can say, or circuit 2 is good. Okay, so this is one way of analysis that I have done in this particular video. Hopefully we'll compare these two circuits in next video in terms of their noise analysis and noise contribution. Okay, and we will see the which circuit is better in terms of noise performance. Okay, so that thing we'll see in the next video. Thank you. This is enough for this video. Thank you.